Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about marginal and conditional distributions. We're going to consider models where we have multiple variables or multiple uncertain quantities that we want to model. And we're going to ask two questions. First, how do we characterize the probabilistic behavior of individual quantities or individual random variables? And second, how do we characterize the conditional behavior of some of the quantities or some of the random variables, given that other quantities or other random variables take some fixed values? The prerequisites for this material are conditional probability and multivariate discrete random variables. Let's remind ourselves what the joint PMF is. The joint PMF gives us all the possible information we might want about the joint behavior of two or more random variables. In this case, we're seeing the joint PMF of two random variables A and B, which is denoted like that. And if we want to know, for example, the probability that A is equal to 3 and at the same time B is equal to 1, then we just look at that entry of the joint PMF and it's equal to 0.05. Okay? If we want the probability that A and B jointly take certain values, for example, any 4 of those values, then we would add those probabilities, and so on and so forth. So now let's imagine that we're interested in the probability that A is equal to a particular value. We don't care about B. So we just, for example, want the probability that A is equal to 1. Then by what I've just said, what we need to do is we need to take a look at where is A is equal to 1. This happens here at the same time that B is equal to 1, here at the same time that B is equal to 2, and here at the same time that B is equal to 3. And now if I'm interested in the probability that A is equal to 1 and I don't care about B, then I need to sum these 3 probabilities. Okay? And in this case, this is 0.05, this is 0.4, and this is 0.1, so the probability that A is equal to 1 is 0.55. If you remember, the probability that A is equal to 1, that's just by definition the PMF of A at 1. So this shows you that you can compute the PMF of the individual random variables using the joint PMF. So we would do that for 1, then we would do it for 2, and then we would do it for 3, and this way we could compute the PMF of A, and we wouldn't worry about B anymore. We don't even need to know what B is doing. We have all the probabilities that we need to describe A. That is called the marginal PMF of A within this probabilistic model. If we didn't have B, then we would just call it the PMF of A. And in fact, the notation is the same. So we don't care about B, we only want the probability that A is equal to A. What did we do now intuitively? Well, we took the union of all the events such that A was equal to the fixed value that we're interested in. We took the union of all possible values of B. What I mean is we took the events A is equal to a fixed value and B is equal to a fixed value, and we take that union over all possible values of B because we only care about this, about A being equal to 1 or to 2 or to 3. Okay, so because these events are disjoint, and we already showed this anyways in the case when we were describing the joint PMF, that you can just add those events to get the probabilities. We just add them, and this shows us that if we add a joint PMF over the variable that we don't care about, in this case B, this yields the PMF of the remaining random variable. That is called marginalization because you obtain the marginal PMF. I will say a little bit later why it's called marginal PMF when we take a look at an example. But yeah, that's how you get the marginal PMF from the joint PMF, by summing over the random variable that you don't care about. Okay. So this is just like a bit of a graphical description. If I want the probability that A is equal to 1, then I'm going to add over the green columns. The probability that A is equal to 2, I'm going to add over the purple columns. The probability that A is equal to 3, I'm going to add over the red columns. and I'm going to get this marginal PMF, and you can check that it's going to add up to 1. It has to add up to 1, right? Because I'm essentially adding these guys here, these guys here, these guys here. Their sum has to add up to 1 because I know that they're if I sum all of them individually, they have to add up to 1 because this is a valid joint PMF. Okay, so let's take a look at an example. Remember this movie data set where we were looking at the ratings obtained by Independence Day and Mission Impossible at the same time. So we're considering users that rated both movies. 1 is the worst rating, 5 is the best rating. And this was the joint PMF that we computed from the data. But now what if I'm only interested in Mission Impossible? Well, if I want to compute the probability that Mission Impossible got a rating of 1, then I have to add over this row. If I'm interested in the probability that Independence Day got a rating of, let's say 3, oops, sorry, I didn't mean to do that. I meant to do this, a rating of 3. Then I have to add over this column. Okay, so the rows, adding over the rows will give me the ratings of Mission Impossible. Adding over the columns will give me the ratings of Independence Day. And by the way, according to Wikipedia at least, this is why it's called marginal PMF, because if I start adding these guys in this direction, maybe I should use that. If I start adding all of these guys, if I start adding all of these guys here, I can start writing the values here in the margin, and apparently that's what people used to do on these tables. That's why it's called the marginal PMF. Again, according to Wikipedia, who knows whether that is true or not. But the point is that we can add them that way, and we get the marginal PMF for Mission Impossible by adding over the rows. Here, for example, we see that about 36% of the people gave it a 3, only around 10% of the people gave it a 5, about 4% of the people gave it a 1. I can do exactly the same thing for Independence Day. As I said, now I will be summing each column. And these are the ratings for Independence Day, which it seemed got better ratings than Mission Impossible. You see here that, for example, the ratings equal to 5 are close to 20%. In comparison with Mission Impossible, I was actually surprised by this. I thought that Mission Impossible would get better ratings, but at the same time, we have who knows what users were in this particular data set. So. Anyways, you probably don't even remember these movies, but they came out when I was a kid, so I actually went to the cinema to watch them. Okay, so we may be interested in the joint behavior of a subset of the random variables that we're considering within a model, not only a single one. Now we have seen what we do if we were interested in the behavior of a single one, but what if we're interested in a couple of them? So here imagine that you have a 4-dimensional random vector, but you only care about the first and the fourth entry. You want to know the probability that the first entry is equal to A, and simultaneously the fourth entry is equal to D, but you don't care about the other two. What do you do? Well, you have to consider the union of all events for which this happens, and that's going to include the other two random variables, but you're going to take the union over all their possible values so that what you want to happen happens. In this case, that the first entry is A and the fourth entry is D. So what they're going to do, you're going to add the joint PMF over all those possibilities. You're going to add the joint PMF over all the possible values of B and C here. So it's exactly the same idea. You take the random variables that you don't care about, in this case the second and third entries, and you sum over them. Here x2 and x3 just represent the range of the second and third entry, all the possible values. Okay, so we're going to look at an example. Maybe I escaped too quickly from that slide. I just want to remind you, you're interested in the first and fourth entry, you sum over the rest, over the second and the third. That's how you compute the marginal joint PMF of the first and fourth entry. That's how you do it. Okay, so let's look at an example where we have more random variables, because in the case of the movies we only have two, so I can't really illustrate that. We're going to look at precipitation in Oregon in 3 weather stations, which are Coos Bay, Corvallis, and John Bay. Okay, and we're interested in the precipitation patterns, if you remember from the other video, in particular whether it rains or not. So 0 is that it doesn't rain, 1 is that it rains. Okay, so this is in Coos Bay, Corvallis, again, it doesn't rain, it rains, and so on and so forth. And remember that what's really important is that we have data that tells us whether it was raining in each of these places at the same time or not. And we use those data to compute the joint PMF. Okay, so for example, this number here tells us that 0.39% of the time it was not raining in Coos Bay, it was raining in Corvallis, and it was raining in John Bay. Okay, just to be clear about what that means. But now, what if we're interested in Coos Bay and Corvallis, but we don't care about John Bay? So for example, we might want the probability that it does not rain in Coos Bay and it does not rain in Corvallis, but we don't care about John Bay. So when does this happen? When does it not rain in Coos Bay and not rain in Corvallis? It happens here when it doesn't rain in John Bay, and it happens here when it rains in John Bay. So what do we need to do? We need to just add up those probabilities. And that's going to give us the probability that it doesn't rain in Coos Bay and it doesn't rain in Corvallis. What if we're interested in the probability that it rains in Coos Bay but it does not rain in Corvallis? Well, we're going to add up this guy and this guy, okay? As I said before, what do? You say, okay, what do I care about, Coos Bay and Corvallis? Let's sum over the stuff that I don't care about, which in this case is John Bay. Okay, and this gives us this joint PMF between Corvallis and Coos Bay. For example, it's raining in both Corvallis and Coos Bay 5.72% of the time. Okay, so now I would like you to think, what are we going to do if we want the joint distribution of Coos Bay and John Bay? Well, we do the same thing. So, for example, the probability that it rains in Coos Bay and it also rains in John Bay. This happens in these 2 cases. So we're going to take these 2 probabilities and we're going to add them up. What if we were interested in whether it does not rain in Coos Bay but it rains in John Bay? We're going to take these probabilities and we're going to add them up, and so on and so forth. That's how we're going to get the joint PMF of John Bay and Coos Bay. What about Corvallis and John Bay? Same idea. For example, doesn't rain in Corvallis, it rains in John Bay. We're going to add up that, and so on and so forth. Again, we add over the variable that we don't care about. What if we only want the probability that it rains in Coos Bay? So we only care about Coos Bay, we don't care about Corvallis and John Bay. What do we do? Well, let's see, for example, we're interested in the probability that it does not rain in Coos Bay. When does that happen? It happens here, when it doesn't rain in Corvallis or John Bay. Here, when it rains in Corvallis but not in John Bay. Here and here. So now we're going to add up all those probabilities. And by the way, here I really recommend that you just pause the video and think about it. I know that I was going a little bit quicker. I should maybe have given you the option to pause the video before getting into it. But from now on, just stop the video and try to do it by yourself. What about if I'm interested in the probability that it rains in Coos Bay? What am I going to do? Well, it's this part, so I'm just going to add up all these guys. Okay, so this is the probabilities that I get if I add up the yellow points that I just showed you and the blue points that I just showed you. It turns out that most of the time it's not raining in Coos Bay, but remember that this is hourly measurement, so it's not that surprising. Like even in places where it rains a lot, you cannot expect it. Like if you look at the actual hours that it's raining, you cannot expect it to be raining that high a percentage of the time. Okay, so what if we're interested in Corvallis? Again, think about it by yourself. But essentially what you're going to do is you're going to see when is it not raining in Corvallis, when is it not raining in Corvallis, here, 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 and here. So add it up. When is it raining in Corvallis? Here, 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 add it up. And it's very easy to see that you're going to get a marginal PMF that is going to add up to 1, because you know that all of these guys anyways add up to 1. Okay, and this is the marginal PMF at Corvallis. What about John Day? Very same thing. I don't want to bore you guys, but yeah, so basically you would add these guys to see when it rains, and these guys to see when it doesn't rain. And actually John Day is drier than Corvallis, and it's towards the interior. I guess that's why. I'm no expert in meteorology, but it's towards the interior, so it's quite a bit drier than Coos Bay and Corvallis. Okay, so now let's shift gears. We already answered how do you characterize individual variables within a model that has many variables. How do you do it? You marginalize by summing over the rest of the random variables. That's essentially, you take the joint PMF, you sum over the rest of the random variables. That's how you do it. Okay, so now let's think about conditional distributions, which is a little bit trickier. So let's assume that someone tells us, hey, you know what? A is equal to 3. We know that A is equal to 3. That means that we know that we are here. Okay? We don't know the value of B. Okay, this is the whole point. B remains uncertain, but we know that A is equal to 3. So it seems to stand to reason that we would just eliminate these guys, right? Because we know that that cannot happen, and we would just keep these values that we have here. Okay, this was not my most beautiful annotation, but basically you would keep these guys here, and you would eliminate these ones. That stands to reason. Okay, so in this case, for example, if A is equal to 3, we would just keep the red columns from the joint PMF, and we would discard the rest. These are the red columns. Is it a valid PMF? Can I just say, oh, you know, this is the PMF of B if A is equal to 3? I'm done. I can go home. So think about it for a moment. The answer is no, because if you add up these values, it's 0.2 plus 0.05 plus 0.05. That doesn't add up to 1, which makes sense, right? Because I know that all of these columns have to add up to 1, so why would a subset add up to 1? This is exactly the same issue that we encountered when we were talking about conditional probabilities. So let me remind you, if we're thinking of the conditional probability of B equal to a certain value, given that A is equal to another value, which is how we define the conditional PMF of B given A, which is what I'm talking about, right? Like A is fixed. Now what is the value of B given a certain value for A? If we look at that conditional probability, then we know that it's the probability of the intersection divided by the probability of A having that particular value. So if we go back here we're just showing the probabilities of the intersections, right? The intersection of A equals 3 and B equals 1, then A equals 3 and B equals 2, and A equals 3 and B equals 3. We're showing just the intersections. We need to normalize them. As we explained when we introduced conditional probabilities, we need to normalize them by dividing by the probability that A is equal to 3 in that case, or otherwise by the probability of their sum. So in this case, we need to fix. So what do? We fix the value of A because we know that's the value taken by the random variable A. And now we need to normalize dividing by the probability of that happening, which is the value of the PMF. In this case, it's the marginal of A at that value, at 3, in the case that we were interested in. Okay, we need to normalize so that we obtain a valid conditional probability. When we put those conditional probabilities together, we obtain a conditional PMF that is conditioned on this value of A. So we do that, we normalize, and boom, we get a valid conditional PMF for B, given that A is equal to 3. I said that a little bit quickly, but the conditional PMF, and this is important, is a valid PMF. First of all, it's non-negative because it's just conditional probabilities, so of course they're non-negative. Second of all, if we sum it over B, let's do that. By the definition, we're summing the joint PMF. So remember that the conditional is just equal to the joint, and then we have to normalize by dividing by the marginal at the value that we're conditioning on. So if we sum the PMF over B, what do we get? What are we doing here? Think about it for a moment. We're marginalizing over B, right? So we're just going to get the probability of A. So this is going to cancel out, and we're going to get 1. Said otherwise, like maybe it's easier to see why it would add up to 1 if we look at our example where we first naively just took the probabilities of the intersection. What are we doing when we divide by the probability of A? We're just dividing by the sum of these guys. So obviously, once we divide by the sum, when you add them up again, they are going to add up to 1, right? If you normalize them so that now they look like this, of course they're going to add up to 1. But that's nice because that means that we obtain a valid PMF. And it's important to remember that it's a valid PMF over B, not over A. And I cannot say that loud enough. It's not a PMF over A. A just tells you what you're conditioning on, that's it. There's no uncertainty left over A, okay? And this is really important. In fact, I want you to think what happens if you sum this thing over A, okay? Over all the possible range of A, what happens? And what happens is, I don't know what happens. It can have any arbitrary value because here, this PMF is only related to B. A is just saying which PMF we need to choose because we have conditioned on A being equal to that particular value. But the PMF is over B, and that's super important. So there's no reason why that would add up to 1. Please remember that. Okay, so let's take a look at an example. Let's imagine that we were interested in users that have rated Mission Impossible with a 1. So those are these users. And now we want to see how those users in particular rate Independence Day. What are we going to do? Remember that this is a joint PMF. We're going to take these guys and we're going to normalize them. We're going to normalize them by their sum, which is exactly the probability that Mission Impossible gets a rating of 1. Okay, so if we do that, this is the value that we get. We get that among people that rated Mission Impossible with a 1, they give a rating, like about 20% of them give a rating of 1 to Independence Day, about 30% give a 2, close to half give a 3, and a little bit less than 10% give a 4, and none of them give a 5 to Independence Day. This conditional PMF allows us to understand how different people rate this movie. So we're going to compare to the marginal. Remember that the marginal is obtained by aggregating, so this kind of tells you how people in general rate Independence Day. Now, if you look at people that didn't like Mission Impossible, they seem to also not like Independence Day as much, right, compared to the general population. As you look towards people that like Mission Impossible more and more, so these are people that give Mission Impossible a 2, people that give Mission Impossible a 3, a 4, a 5. Then what you see is that increasingly they give better and better ratings to Independence Day. Why does this happen? This could happen because some people are just more generous than other people. So it might actually not be that the movies are necessarily connected, right? It might be some people just like giving 4s and 5s because they feel bad otherwise, or it might be that the movies are very connected and they're kind of similar style of movies, and people that like Mission Impossible tend to also like Independence Day. Okay, so what if we want the conditional joint PMF of several variables given other variables? So imagine that I have a 4-dimensional random vector, and I know that the first and the fourth entries are equal to A and D, and now I'm wondering what's up with the rest of the entries, right? I'm wondering what's the probability that the second entry is a B and the third entry is a C, given that the first and fourth entries are fixed? Well, we apply conditional probabilities. This is the conditional probability that the second and third entries take those values, given that the first and fourth take those values. Okay, maybe I'll color code this a little bit. And what is that equal to? Well, the joint PMF at those values divided by the probability that we're conditioning on. And again, the point of this is that it normalizes it so that it becomes a valid joint PMF. Oh, I just saw that I try not to do this, but I cut, like there it should say several variables. Sorry about that. Okay, and there it is again. I guess here I was just, when I was making the slides, I gave up at some point. Okay, so by the definition of conditional probability, conditional PMF, we get something analogous to the chain rule, but for random variables, because this is defined as the joint. Oh, sorry about when I try to write small letters, my handwriting just degrades. Okay, and we're dividing by the joint. So now I can just take this guy and multiply on that side, and I get a nice chain rule for random variables. If I want to express the joint in terms of the marginal and the conditionals, I just take the marginal at that point and multiply by the conditional, where I'm conditioning on the same one as the marginal. Okay, that's important. Just as in the case of events, I can do this in any order. And the order is going to be very important both in homework problems and in real life, because as we will see, not in this video, but in a future video, it's often very necessary to assume conditional independence assumptions. We'll get to that. But the point is that those assumptions are going to play in what order you apply the chain rule. When you have many random variables or entries in a random vector, it's exactly the same idea. Again, it's the same idea as when we were talking about the chain rule of multiple events. What you do is, these guys, by the way, are just the entries. Okay, these are just the D entries of this guy. And these guys are the random variables that are the entries of the random vector, just to clarify. And what we do is, we take one out, and then we always condition on that one. Then we take a second one out, x2 in this case, and then we always condition on that one too. So x2 should be in there, and x2 is going to be in there, and so on and so forth. Okay, exactly like what we did when we're talking about the chain rule of events. And again, you can do it in any order, and you have to be clever about the order when you're doing probabilistic modeling or homework problems. Okay, so let's take a look at an example. Let's imagine that we know that John Day, it does not rain in John Day. So what's up with Corvallis and Coos Bay? So what we're saying here is that we know that it did not rain in John Day. So basically that means that this didn't happen, this didn't happen, this didn't happen, and this didn't happen. So we are left with this, 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 and this. But of course, these guys are not going to add up to 1 because we're eliminating some stuff. We know that the whole sum is 1. So we have to normalize to obtain a valid conditional joint PMF. So what we would do is we would add all of these values, which are equal to what? They're just equal to the probability that John Day, it does not rain in John Day. So this is consistent with the definition that we had before. We're going to normalize according to that value, and we're going to get a valid joint PMF for it for Coos Bay and Corvallis. Okay, here we see that there's not a dramatic difference in the joint when it doesn't rain in between the joint and the marginal. Between the joint PM, the marginal joint PMF and the conditional joint PMF when it doesn't rain on John Day. In John Day. Let's see what happens let's see if this is also true when it does rain in John Day. So now we're going to take these values here, and we're going to normalize them, and that's going to give us the conditional, and we see that actually here things change a lot. So it's much more likely to rain in Corvallis and Coos Bay, you see it here, right? Compare this value to this, or even this value to this, when it actually rains in John Day. So here the distribution, the joint distribution of Corvallis and Coos Bay actually changes quite a bit. Okay, what if we condition on two, like if we fix two of the random variables? So for example, here we know that it did not rain in Corvallis, it did not rain in John Day. Okay, so here we end up with this probability. Oh, sorry. Yeah, I was getting confused myself. As you can see, this is quite confusing, so pay attention. And again, maybe I should have gone a little bit slower, but try to stop, after I ask the question and try to do it by yourself. So here there's two options, right? Like either it rains in Coos Bay or it doesn't. So we just have, this is the probability that it doesn't rain in Coos Bay if this happens. This is the probability that it does rain in Coos Bay if this happens. But now if we want the conditional probability, we have to divide by the probability that this happens so that we get a valid conditional PMF. How do we do that? We just need to add this guy and this guy, right? When we do that, we get the the conditional PMF of Coos Bay, given that it doesn't rain in Corvallis and it doesn't rain in John Day. And we can compare it to the marginal, where we're just looking at the probability of Coos Bay on its own. We're not conditioning on anything. Okay, we can repeat the process for different combinations here. And we see that there's not such a big difference maybe when, John Day changes, but when Corvallis changes, the change is pretty dramatic. In fact, at some point, if it's raining in Corvallis, it seems that it's more likely for it to rain in Coos Bay than not. So that's really like a dramatic change because of conditioning. So then maybe motivated by that, let's take a look at what happens in Coos Bay when it doesn't rain in Corvallis or when it rains in Corvallis. So here, things start to get a little bit tricky, so pay attention. Well, first, actually, maybe you think about how you would go about doing it. So pause and think about it. And now I will do it. So we're saying that we're interested in fixing that it doesn't rain in Corvallis, okay? And we want to see what happens in Coos Bay in that case. So that happens, these are the values for which it doesn't rain in Corvallis. And now we're going to, we might be interested in the probability that it does not rain in Coos Bay. So how are we going to compute the conditional probability that it does not rain in Coos Bay given that it rains in Corvallis? We're going to take these two values, right? And we're going to have to add them up together. And that's going to give us a certain value. But that's not a normalized probability, right? We also have to consider the probability that it does rain. I'm going to use a different color. Maybe I'll change to green. That it does rain in Coos Bay. Then for the probability that it does rain in Coos Bay conditioned on that, we're going to add these two values. So, and now we have to normalize, right? We're going to have to normalize by the sum of this and this, okay? We're going to have to normalize by the sum of that and that to get a valid conditional PMF of Coos Bay given Corvallis equals to 0. Okay, I hope that makes sense. It's going to look like this, okay? So this is what we're going to get. Now, we could repeat this for Corvallis equals to 1. And then what we would do, so maybe think about it. I'm repeating this because I think this one is a little bit trickier. So let's just go through it very quickly. Now again, we're, what if Corvallis is equal to 1? Then what we would do is we would fix Corvallis equal to 1. And we have two options, right? Like Coos Bay is equal to 0. In that case, we would aggregate these two guys. And Coos Bay is equal to 1. In that case, we would aggregate those two guys. And we still need to normalize in order to ensure that the conditional PMF is a valid PMF by dividing by the probability that it rains in Corvallis, basically, which is the sum of this and this. So like this, we would get this. And here we do see that the difference is actually very dramatic. Okay, like in Coos Bay, if it doesn't rain in Corvallis, it's very likely that it won't rain. If it does rain in Corvallis, the probability that it rains is actually higher. It's about 60%. We can repeat the same thing for John Day, and I encourage you to do it. And we see that the rain in Coos Bay also depends on John Day, but not as dramatically as in Corvallis. Okay, so talking about how dramatic the dependence is or not, let's take a look at two other stations. One in Rhode Island. If you notice this point here, that's just where I'm located. And I got this from Google Maps. I didn't know how to remove that dot, but anyways. And this is another station in Hilo. So we're going to be interested in Hawaii, Big Island. So we're going to be interested in comparing like precipitation in Rhode Island and Hawaii. What's the relationship between them? Okay, so we compute the marginal PMF of precipitation in Hawaii. You actually see that it rains a fair bit. It's one of the stations where I saw that it rained the most. And now we're going to compute the conditional in the way that I showed you previously. Condition on Rhode Island, on Kingston. When it doesn't rain in Kingston, it doesn't seem to make a difference for Hawaii. When it rains in Kingston, it doesn't make a difference for Hawaii. And there's a very slight difference, but you can't even see it on the graphs. And it could be just because of sampling error, like when we were looking at independence of events. Okay, so what if I look at the distribution of Kingston? So whether it's raining in Rhode Island, this is the marginal PMF. What if it's not raining in Hawaii? Looks pretty much the same. What if it's raining in Hawaii? Looks pretty much the same. This makes sense, right? Because they're so far away. And in Hawaii, there's no seasons like there are in Rhode Island, because that could connect them even if they're very far away. Here, what we're seeing is that these two random variables are essentially independent. We say that two random variables, A and B, are independent if our uncertainty about A does not change when information about B is revealed, or vice versa. This is captured in the same way as with independence between events. In independence between events, we saw that the conditional was equal to the probability of the event, or equivalently, the intersection was equal to the product. In independence between random variables, the conditional PMF is actually just a conditional probability of an event related to one random variable conditioned on another event related to the other random variable. If any such events satisfy independence, then we say that the two random variables are independent. Equivalently, if the conditional PMF is always equal to the marginal PMF, these random variables are independent. Because of the chain rule, this is the same as saying that the joint PMF is always going to factorize into the product of the marginal PMFs for any possible values of A and B. When you go to several random variables, the idea is exactly the same, or the entries of a random vector. They're going to be independent if the joint factorizes into the products of the marginals, for the same reason I explained before. And this must happen for all possible values of the entries. Okay, in that case, we say that the random variables are independent, and if you want an intuitive illustration, it's precipitation in Hawaii against precipitation in Rhode Island. Let's go back to Coos Bay and John Day, because they're going to allow us to illustrate conditional independence, which is a bit trickier. So we saw that if we look at the marginal precipitation in Coos Bay and we compare it to the conditional when it doesn't rain or when it rains in John Day, we do see a difference, especially here. Okay? But when we look at the dependence on Corvallis, the dependence is much more dramatic. So we could maybe think that perhaps if we know about Corvallis, then John Day doesn't matter as much, which, if you remember, this is what is captured by conditional independence. So we could compare the conditional PMF given that it doesn't rain in Corvallis with the conditional PMF given that it doesn't rain in Corvallis and it doesn't rain in Coos Bay, in John Day, and we see that they're actually very similar. And also with the conditional PMF conditioned on it doesn't rain in Corvallis and it does rain in John Day. So this is not a perfect example because here you see a slight difference. So conditional independence would occur if these were exactly the same. But I looked through a lot of stations. This is what I found. Real data is actually messy, and this actually illustrates an important point, which is that true conditional independence, when things are actually related, is not easy to find, even though we assume it all the time. And you might be like, oh, so are we stupid to assume it all the time? Stay tuned for the next video where we explain that it's actually necessary. But anyways, I don't want to digress too much. The point here is that it seems that there's not such a big difference when we have conditioned on Corvallis and then we change John Day. Let's take a look at what happens when it rains in Corvallis. As we see, like the distribution in Coos Bay changes dramatically. What if on top of that it doesn't rain in John Day? It's almost essentially the same. If it also rains in John Day, it does change a little bit. So these things are not completely conditional independence, but if you imagine for a moment that this wouldn't change, then we would have conditional independence between John Day and Coos Bay given Corvallis. And this makes some sense if you look at where these things are located, because John Day is all the way here over the interior, and Coos Bay and Corvallis are very close. And in fact, Corvallis is kind of a little bit in between Coos Bay and John Day, a little more towards the interior than Coos Bay. So if you know what's going on in Corvallis, this already gives you a lot of information about what is going on in John Day. So this conditional independence makes some sense. Again, it doesn't hold exactly if you actually look at the data. So we already saw that two events are conditionally independent if, given a third event, the conditional doesn't change. So we're conditioning on C, and then conditioning on B just doesn't matter. So in this case, C would be Corvallis in our example, and John Day would be B. It doesn't matter if you condition on John Day or not, which is not completely true, but almost. By the chain rule, this is equivalent to saying that you're going to get this factorization where the probability of the intersection given the third event is equal to the product. And again, we can translate this into a definition of conditional independence for random variables, where this stuff just happens all over the place. I'll show you in the next slide. I forgot to say that, and this is very important. Conditional independence does not imply independence or vice versa. We gave an illustration of this for events. You can just translate that immediately into random variables. Because independence for random variables is stronger, and conditional independence for random variables is stronger. We're saying that A and B are conditionally independent, given C, if our uncertainty about A does not change when information about B is revealed, as long as the value of C is known, and that holds for any possible values that A, B, and C can take. Okay, so that's kind of a conditional independence of many, many events. That's what I mean by saying that it's stronger. So the conditional PMF is always going to be equal to the conditional joint PMF of A and B given C is always going to be equal to the product of the conditional marginal PMFs of A and B for all possible values. Okay, and equivalently, this is this is exactly the same, right? Like I don't know what I was thinking here. So, okay, equivalently, forget about this. Here, I don't know what I was thinking, and I don't want to re-record this, so this will be our little secret. What have we learned? We have learned to compute marginal PMFs that characterize the distribution of individual variables or subsets of variables within a model that has more variables. We have shown you how to compute conditional PMFs that characterize the conditional behavior when we fix some other variables. And we have defined independence and conditional independence. Thank you very much.